Greetings and welcome again to this course. Last class we had particularly seen finite volume strategy for convection and diffusion term put together, and we mentioned the need for knowing different types of interpolation required for convection term and evaluating flux at control volume phases. We also looked at in detail about CD approximation, and we took an example problem of flow through a backward facing step. We understand in the same flow, even in the same geometry, you have a different flow regime, flow going in the reverse direction. Hence, there is a need to take the flow physics represented appropriately in the evaluation of flux at control volume phases. For the sake of continuity, again we reproduce control volume, finite volume mesh and terminologies used. The last class we had this discretized equation including convection term. So, convection term is on the left side and diffusion term on the right side. We notice that convection term to be evaluated at phase E and W. Similarly, diffusion flux to be evaluated at phase E and W, and this is for 1D situation. So, correct evaluation of variable and its derivative at the phase is very important. As I explained with the help of an illustration that should correctly represent the flow physics, and it also affects accuracy as well as to some extent stability. We are going to discuss 5 different approximation method to get flux or function value at the phase. They are central approximation, pure Upwind approximation, hybrid scheme, power law scheme and quick approximation. We have already seen central approximation, and we noticed that central approximation does not recognize the direction of the flow, it takes equal weightage from the neighboring nodes. For example, in this case if the flow is from left to right, and to evaluate variable at the phase west, then the neighboring nodes are P and W, it takes equal weightage from both these two nodes. Similarly, for other situation, if the flow is from right to left, then it takes correspondingly neighboring nodes and then gives equal weightage, that is for the uniform mesh. If it is non-uniform mesh, then you take appropriate weightage, it does not factor the flow direction. In the case of next scheme, that is pure Upwind, then phi value at the phases are determined based on the direction nature of the convection velocity u. If you can recall the illustration I explained in the last class, backward facing step, I was particularly mentioning about the coordinate definition. So, with respect to the coordinate definition, then convection velocity direction also is decided. This scheme which decided based on the direction of the convection velocity u is what is known as pure upwinding. Here the nodal value information upstream of the point of node of interest is considered to define value at the phase. For example, we will take the same illustration that we had just now shown for central differential scheme. The flow is from left to right, and to evaluate variable at this phase W, it is given same value as variable at the upstream of the phase. So, in this case upstream of this phase node is at capital W, that is this node. So, variable available at this node is given, and variable at this phase is same as variable at this node. So, in this case phi at W equal to phi at node W. Similarly, for east phase, upstream of this east phase is node P for the direction that we have shown, that is left to right. So, phi at E is same as phi at P. Now, you can see very clearly the difference between central approximation and pure upwinding. Let us take another case, that is flow is from right to left as shown here. So, phi at east is same as phi at east node, because for this phase, for the direction of the flow that is shown, the upstream node is E. Similarly, if you come to the other side, for this phase, upstream node is interest node P itself for the direction of the flow that we have shown. That is why it is phi at west phase is same as phi at node. So, you can see the difference between central type of approximation and pure upwinding. It is called pure upwinding because later we are going to see some kind of a weighted average between pure upwinding and upstream biased upwinding. Okay. Now, as we did before, convective flux is defined as rho u with the symbol F c. Now, we have this switching. If the flow is from left to right, then we take the upstream node. If the flow is from right to left, you take corresponding upstream node. In a problem, you have some regions where the flow is from left to right, in some other region you have flow right to left. Using the same code, we should have the provision check the convection velocity direction and switch the corresponding upstream side, and that is explained in this slide. So, for example, it is effected in the coefficient in the neighboring nodes. So, it is A e and A w are the two neighboring nodes for the node of interest P. If the flow is from left to right, that is the convection velocity is positive for the definition of coordinate that you have chosen, then u is positive. So, F c is also positive. So, we write F c w is greater than 0 and F c e greater than 0, then we have coefficient defined accordingly for the east phase and east node and for west node. If the flow is from right to left, then for the coordinate definition that you have chosen, it becomes negative, then corresponding F c goes to negative. That is why we have condition if F c w less than 0 and F c e less than 0, then we rewrite the coefficient accordingly. Okay. So, this switching depending on the direction of the velocity, you can actually incorporate in the code also. You can actually have a check condition and then you can switch between one scheme to the another scheme or upstream node accordingly. So, in more general form, so to put these two things together, because in a code you will have only a continuous line or one line representing all the situation, we write A e as F d w plus max of F c w comma 0. So, this will take maximum of these two values. 0 is the limit, and if it is positive for the flow from left to right, F c w is positive. So, that will be taken and it added to the F d w and you get back that original coefficient expression. To get other condition, then we again write here if the flow is from right to left, then F c e will be negative and minus F c e will be positive and greater than 1. So, we have again condition max of 0 comma minus F c e and the diffusion coefficient contribution. So, this condition, that is defining max of 0 and other value minus FCE or FCW, will automatically switch inside the code. We do not have to do anything manually externally. So, next we will see central difference scheme is second order accurate, but it does not reflect the convection, whereas upwind scheme, pure upwind scheme that we have just now seen is first order accurate. As we have seen, it only takes the nodal value upstream of the phase for the corresponding or the respective direction of the flow, whereas it does reflects the convection of the flow. Okay. So, now the obvious question whether we can take or utilize advantages of both and put it in one particular scheme. Okay. So, for both accuracy can be improved either by considering more or finer mesh points, that is what we have shown is kind of second order approximation for central scheme, that is you take one node on the left, one node on the right and take average. You can actually extend it by taking extra node on either side. So, it can be a 2 node on one side, 2 node on the other side and take average accordingly. So, that becomes next order of accuracy in central difference scheme. Similarly, for pure upwinding, instead of taking just one node immediately upstream of the phase, you can actually take one more node. So, in this case for example, we for the phase at W, we considered node value at W. In addition, you can consider node available at WW. So, you can actually increase the order of accuracy by considering more number of points. However, still the property remains the same, that is they reflect convection, other one does not reflect the convection, but order is always higher. So, I just give a illustration, this is just illustration for a particular problem, and what is shown here is exact solution, that is by one particular, what is shown here is exact solution vertically. If you use pure upwinding with a mesh size 50 by 50, then you get a solution as shown by blue color. If you have used lesser mesh size for the same pure upwinding 10 by 10 size, then the black color line that shown here is a result. If you have made the mesh much finer, say in this case it is 100 by 100, then you get a solution as shown by this color. Yeah. Whatever it is, the pure upwinding, it smears the solution and you will never get to reach the exact solution, in spite of the fact that to increase the mesh size twice from 50 by 50 to 100 by 100, you still have some diffusion here, exact solution is not obtained. Whereas, the central scheme will try to capture this peak. Hence, there is a thought process whether you can combine advantage of both the scheme. Okay. Alternatively, one can switch between two scheme, that is central or pure upwinding, either based on some weightage. Okay. So, you decide if the flow is less, then you can switch, or if the flow is normal, then you can go to central difference scheme, or you can take you can calculate first by central difference scheme, second by pure upwinding and consider equal weightage to both and then combine them. So, this is what is known as a hybrid scheme. Combining both the methods, calculate the flux by both central difference scheme and upwind method, either you can give a equal weightage to both, or you can decide the weightage according to the problem. Any one of the method falls under category what is known as a hybrid scheme. now how to switch between the two? We have a number called Peclet number, which is the ratio of convective flux to the diffusive flux, and that is given by the letter symbol P e. It is equal to F c by F d. P e is evaluated for each cell phase, and then it decides whether one has to switch between central differential scheme, pure upwinding or the hybrid type, depending on the condition that you are using for evaluation. So, for example, if P e is less than or equal to 2, which means it is F c and F d ratio. So, you can think of F P e is less than 2, then it is a central approximation that is used. If P e is greater than 2, which means the numerator is very high and denominator is very less, both these possibilities are there. That means convection is dominating, hence you can switch to pure upwinding. So, this condition also you can enforce or you can incorporate in your own code, decide based on Peclet number and define the Peclet number as ratio of convective flux to the diffusive flux. There is one more special type of treatment, what is known as a power law scheme, and here we are switching between two schemes. The two schemes are slightly different. The one scheme is a hybrid of CD and pure upwinding, the other scheme is pure upwinding itself. So, we have option, you consider mix of hybrid and mix of CD and pure upwinding as one option, or it is only pure upwinding. So, this is what is known as a power law scheme, and in this scheme diffusion is set to 0 if the absolute value of Peclet number exceeds 10. So, in the previous slide we had put a condition P greater than or greater than 2, then it becomes pure upwinding. Now, this is condition above that condition. So, if absolute of P e, that means you take only the magnitude, exceeds 10, then it is purely convection problem, diffusion has no role, hence the diffusion is set to 0 and we have only pure upwinding scheme applied. So, mathematically you can have the expression P e within the limit from 0 to 10, the flux is evaluated by polynomial expression as given here. For example, flux crossing the east phase is given by A e equal to F c e and the coefficient phi at east node minus beta e phi at east node minus phi at p node, etc. And this is for condition P e between 0 to 10, where this beta is a coefficient which is actually the speciality of this scheme, what is known as the power law scheme. There you write beta is given as 1 minus 0.1 P e. Again we are evaluating P at every phase. So, here P is evaluated for east phase, because we are just explaining for east phase. So, 1 minus 0.1 P e evaluated the east phase to the power of 5 divided by P e evaluated east phase. Just observe that if you substitute the limiting condition that P e is equal to 10, then 1 minus 0.1 into 10, it becomes 0 almost. So, that is actually what is used here, right. It becomes purely upwinding, right. So, this part beta e is 0 and F c e is purely phi at e. So, that is a pure upwinding, okay. That is what is shown here. For value definitely greater than 10, then A e is F c e and to phi from the node E. If the value of P is less than 10, then you have some fraction value here beta, and that goes into this value beta as some fraction value, for example, you say 0.9. Then this is pure upwinding, phi e is pure upwinding first term, the second term is kind of central differencing. So, this has a combination of pure upwinding and central differencing type of evaluation. So, that is why I said it is a combination hybrid between two schemes, that is hybrid of CD and pure upwinding and pure upwinding. Okay. Next scheme that we are going to see is quadratic upwind scheme, and in short form it is called QUIC. So, what it does, it takes 3 point upstream of the node and give a weightage to the contribution from each node. So, it is uses 3 point upstream weighted quadratic interpolation for cell phase values. Now, why the thought has come? We noticed in the from previous lectures, central differencing type of approximation takes values from neighboring nodes and give a equal weightage, whereas a pure upwinding takes the values from the upstream node. Now, if you fit a quadratic among the 3 nodes, then it is a kind of biasing based on the direction of the flow. Okay. Let us see how to do with a little more detail. A quadratic curve is fit through 3 nodes. Now, how these 3 nodes are chosen is important, one on each side of the interest. So, in this, for example, in the case of west phase, for the flow going from left to right, one on each side is node P and node W, and one more node in the direction of the flow. So, if the flow is from left to right, again west of west, that is W W is additional node. Okay. We will explain this again. This falls under the category what is known as the upwind biased scheme. So, we have a central differencing scheme, we have a pure upwinding scheme, we have a hybrid scheme, we have power law scheme. Now, we have a upwind biased scheme. So, the scheme is kind of central, but it is not pure upwinding, it is a mix of both. So, it is upwind biased scheme. Okay. Let us look at this illustration. For example, phi at W at this phase, then we have a node P, immediate node on the right and node W on the left. So, these two are on either side for this particular phase. Then the flow is from left to right. So, u w subscript W is a convection velocity, it is positive. So, for this convection velocity condition, the upstream condition is node W W. So, we consider node W W, W and node P, and we try to fit a quadratic curve to these 3 nodes with some weightage. So, that is what is shown in the expression here. Phi at the west phase is alpha times phi at W, alpha 2 times phi at P and alpha 3 times phi at W W, if the flow is from left to right, that is u w is greater than 0. Now, let us take the next case when the flow is from left to right and on the east phase, if u e is greater than 0, then the flow is from left to right, phi at E is evaluated for phi at E, 2 adjacent nodes are east node and P node and one more upstream node in the direction of the flow. So, here the flow is from left to right. For that case, one more node in the upstream is actually W. So, the expression for phi at E is equal to alpha 4 phi at P plus alpha 5 phi at E plus alpha 6 phi at W. Now, coefficients alpha 1 to alpha 6 are to be evaluated. So, in today's class we have seen different kinds of interpolation, mathematical expression, how to implement them, details behind each of this scheme. Okay. We get a complete feeling of the effect of central differencing scheme, pure upwinding, upwind bias, hybrid scheme. Now, it is possible to implement all these schemes in one particular code. All that you have to do is switching based on condition. Okay. Most of these commercial softwares have a similar provision, depending on the choice that you select in the option, then it for the same convection term calculation they switch the scheme. Okay. We come to end of this class. In the next class, we will explain all the scheme with the help of an illustration. Thank you.